Hello, everyone, and welcome back to CSE 373. This is probably the last time you'll see me or hear me say this in video form. This is our last pre-recorded lecture of the quarter. Next week, we have our TA-led review session, and Wednesday is kind of a course wrap-up, which I'm going to do live during our class session, which means that this is our last pre-recorded lecture that you're watching. Now, this topic that I want to cover today is this interesting kind of niche data structure called tries, and it's an optional topic in 373, so it's not going to be something that we're going to put on an exercise or on an exam, but I think it's an interesting topic, so I wanted to give us a chance to explore this thing, but this is not part of like the required course content. So during the class session for today's lecture, we're going to go ahead and just do a Q&A session like our other optional classes rather than having established practice problems. So because this is an optional lecture, I also don't have solid learning objectives. It's just like I want to show you something cool that you might run into out there in the world. It's a useful thing to know. So I'm going to introduce this data structure called tries. Before I introduce kind of what it is, how to use it, I want to introduce what the problem it's supposed to solve and why it solves it. In this video, we're going to talk at a high level of like, what is this data structure supposed to represent? In our next video, we'll talk about how do you implement it concretely. So when we want to use one of these structures is to try to solve a problem that we're all fairly familiar with, which is a problem of autocomplete. Say you're on a search engine like Google or I like DuckDuckGo. If you type in some query, it shows you a bunch of suggested queries based off what you typed in originally. Now, you could imagine if you put your 373 cap on, I guess I'm wearing a cap right now, you put your 373 cap on and you'd ask, how would DuckDuckGo or Google or whoever implement something like that? Well, they probably have a set of all possible queries that people have made. So look at all the queries that have been made before, maybe put those in a set of strings. And then if I start typing in data structures and algorithms, they might go through their entire set of queries and find all the ones that start with data structures and algorithms. Now, you as an almost 373 graduate know, well, if there are n queries in total, then that autocomplete function would take something like O of n time. So the question here is there another data structure or another way I could represent this data to make this autocomplete task more efficient, so I don't have to search over every possible string, so that it's organized such that it's able to find me some kind of string that matches a given prefix. So the formal problem we're interested in is given a prefix of a string, find all of the strings in a set of possible strings that have that given prefix. And to make it a little bit more concrete of everything I was just talking about is we already know some data structures that we could try to use to solve this problem. We could just use our implementations for a set, namely a binary search tree of strings or a hash table of strings. And as I just mentioned, you can search through the whole set of strings and just find all of the ones that match the given prefix. Now, what I am going to suggest is a different way of organizing the data to help us with this prefix notion of trying to find all of the strings that start with a query, like PA. So this kind of weird, different way of representing the data is going to be representing a data structure that we call a trie. The idea of a trie, spelled T-R-I-E, or the abstract idea, is to represent a tree. So it's going to be a tree kind of like a binary search tree. But instead of each node representing a single word, each node is going to represent a single letter. And a word in our set, like the word aqua, is going to be represented by a path of nodes where each node is a particular letter. So the word aqua is represented in this trie as the path from the start string, the empty string, to A, to Q, to U, to A. So each node corresponds to a single letter. A word corresponds to a path from the start to the end of a word. Now, the reason we're going to represent it in this way is it lets us unify words with the same prefix. So for example, in this set, I represent the word dad and data. And the way I can try to represent this in a trie is that DA, D for dad, and DATA for data share the common prefix that they share, the DA part. And so we want to represent this structure so that all things with common prefixes have common ancestors in this tree. So we call this specialized character by character tree. We call that a trie. So again, this is an abstract picture of a trie. This may or may not actually be how we implement it. That's kind of the focus of our second video. But this is an abstract idea. I have a tree where each node corresponds to a single character. Now, one of the nice things about this representation is if I have a set of words, sometimes we call this our dictionary. So my dictionary of like the possible queries could be A, aqua, dad, data, day, days. Then I have kind of, for each of those words, since they're strings, they have indices. And this trie is kind of organized that each level of the tree corresponds to a single index of that string. So for example, all of the possible characters that appear at index 0 kind of are the first level underneath. And then all the second characters are the next level, all the third characters are the next, and all the fourth characters afterwards. You can imagine the height of this tree is going to be as tall as the longest word. But hopefully we should be able to save a lot of memory. If there's a lot of shared prefixes, we can represent them without having to duplicate all the data for things that start with DA. Now, one important thing about this representation is that if we're representing kind of words as a path from the start down to a node, we need to know which paths are valid that lead to valid words in our dictionary and which ones don't. So for example, how do I know that A is a word in my dictionary, but AQ is not? So we need one extra piece of information. We need to mark each node with a Boolean indicating whether it's a valid stop node. So all of the valid words in my dictionary, A, aqua, dad, data, day, days, all of their last characters should be marked with a true in this kind of Boolean flag. And so now when I kind of am trying to search for a word like aqua, I start at the top and I search for, go down to A because aqua starts with A, and then Q, and then U, and then A. And since I ended at a node that's blue, I know that aqua was in my dictionary. But for example, if I'm searching for the word dads with an S at the end, then that's going to say that it's not in my dictionary because we start with D and then A and then D, but then we try to find where the S is at the end of dads and we say, oh, well, I'm going to like fall off the trie. So we're going to need some kind of logic of keeping track of how we do these searches and knowing if we land on a node that indicates a valid word. So we know that it is a valid word in our dictionary. So this, as I was kind of alluding to, this abstract trie, this kind of representation of our data, if you're trying to find if a word is contained in your dictionary, then you kind of start at the top and work your way down following the letters of your word. So always if your word starts with an A, then you go down the A path, and then you keep going down letter by letter, following all the branches according to whichever letter you're at in your string, until you run out of nodes or you run out of string to search for. So you find a hit, meaning that you found a valid value in your dictionary, if you land on a blue node and you don't have any other characters to search for. But a miss, meaning it's not in our set of words in the dictionary, is if we end at a node that's not blue, meaning that we don't call it a key, it's not a key in our dictionary, then that's a miss, meaning that we didn't find something, we should return false. Or if we fall off the trie, meaning that I kind of have extra characters left over in my search, but I can't go down any further in the nodes. So let's do some example queries. So data, we start with D, then go A, then go T, then go A. And since we don't have any other characters left, we say it's a hit, we return true. And we had to check 4 nodes to do that. Now, if I search for DA, I start and go down D, go down A, And since I don't have any other characters left, I'm at a non-key. It's not marked as true. I return false. DA was not in my dictionary, which is correct. If you look at the top up here, DA is not in that dictionary. So we always kind of use this kind of weirdly specialized tree structure that knows like it will have many possible children, maybe one for each character. And we always follow the right path. We always choose the child based off the character at the front of the word we're looking at right now. So just to keep going, we talked about if you just search for A, we'd start at the beginning and go to the A branch because there's an A character. And then we say, okay, well, this is a key, so we return true because there's no other characters. And then dubs, if we did D, and then we tried to take a U, but we don't have a U child, we'd fall off the try and have to return false. Now, here's one of the amazing things about representing a set of strings with a try is imagine we had n words in this dictionary. In this case, n was 6. But the amount of searching we did not depend on n. The runtime of these contains methods is based off the height of the tree. But unlike a binary search tree that has height that's logarithmic in the number of values in it, n, the height of this tree is based off the longest length of the longest string. And so we'd say that the runtime for contains here in a set of dictionary of a set of words with n keys at most length L is actually theta of L. Now, it's important to pause for a second and realize how cool that is. Although it doesn't sound like a cool statement, we just made a data structure that no matter how many words are in it, that has a contains search function that does not depend on n. If you think about like the English dictionary, there are lots and lots of words in it, but the longest one probably only has like 20, at most 40 characters in it, if it's like maybe a really long name of like chemical. Like the length of words is usually bounded, but the number of words is really, really large. And now we have essentially constant time lookup because it depends on the length of the string rather than the number of words. That's awesome. This is the first data structure we've really seen, besides hashing, that kind of ignores the amount of data in it. And this is not like in the hashing sense, like where it's in practice O of 1, but worst case, you'll run into this O of n runtime. No. This never depends on n unless the length of your strings also scales with n, which there are not a lot of real life scenarios where you have a word that's on the order long of the entire dictionary. It's just usually not the case. I guess it could happen, but it's not really going to happen. So these structures are really good for kind of replacing set of strings, but they also do a really good job addressing this problem I mentioned earlier, which is trying to find all of the strings that match some prefix. So tries also do a really good job if you had some operations like find all of the keys in the dictionary that start with a given prefix. And it also does a good job at trying to find kind of what prefixes are available in my trie that match a particular word. So we're going to focus mostly on this keysWithPrefix operation to support some autocomplete feature. So trying to find all of the words that start with some sequence of characters. So if we search for day, it would return day and days because those are all the keys in our dictionary, our small 6-word dictionary that start with day. So to do this, we have to implement this kind of operation that we call collect. So it takes a set, it's in some sense like our key set operation on a set. You can imagine at first, our first version of collect is just return all of the valid words in our dictionary from this try. And it's really just a traversal down our tree, trying to find all of the keys, finding all the nodes that are marked as blue, and kind of building up the path along the way. And so I have some kind of pseudocode here that describes this collect operation. It kind of loops over all of the initial children. And the big tricky thing, in some sense, is it is in some sense just a graph traversal. It's just a depth first search. But the trick is you keep track of what's the string I've built up so far. Like when I'm traversing down A and then Q and then U and then A, I'm like building up a string aqua. And then whenever I find a key, I add that string to my set of keys I'm building up right now, my list of keys. So that's the big idea with collect. And the nice thing about this kind of notion of just finding all of the words is it provides this really natural extension to finding all of the words that start with a given prefix, where that now you can actually go through and say, if you want to find all the things that start with day, you could just run this collect helper, but start at the node DA or DAY, whatever you're searching for. So just start your search somewhere else and then find all of the words that are children of this kind of start node. So that's one of the nice reasons of using a structure like this, is it just kind of provides for free, in some sense, access to all of the things that start with a particular prefix. You don't have to search all of the strings in the dictionary. You just have to search the ones that start with the prefix already. So now if you're thinking about an autocomplete function, you can imagine how we use a trie for that. We just make this kind of tree structure that has all of our queries as kind of paths along the tree. And one other additional thing that we didn't really talk about is you can imagine also labeling each node that corresponds to a query as some sort of relevance, meaning that most search queries or most search engines usually there are probably lots of valid queries that match a given prefix, but they only show like the top 10. You can imagine doing something like that here. The idea being is you modify your implementation of the trie to also keep track of like what's the relevance score and maybe compute that based off the number of times that's clicked. Or maybe you have some kind of learning algorithm that tries to predict relevance. But the idea is you could just find all of the things that start with this given string and have the highest relevance. So that's kind of the high level, big picture idea. What I want us to talk about in the next video is how do we actually implement this idea of this kind of graph that has this path for all of the words in the dictionary. How do we build that up? And how do we actually represent that so we can query it later? But that's the focus of our next video.